We are going to be looking at systems of linear equations, and the first method that we will be focusing on is graphing. First, a few definitions. Two or more linear equations make up what we call a system of linear equations. Think about a system as things that are working with each other. So a system of linear equations is one line that is also occurring with another line, and so how are they working together? A solution to a system of equations in two variables is an ordered pair that is a solution to each individual equation. So that's a very important point to make right there. Every line has infinite points. But for a system of equations in two variables to have a solution, that means one line has a solution, an ordered pair, and the other line has the same solution or ordered pair. That's what composes a solution of the system. Both lines share a same solution, a shared point. So graphically, the solution to a system of equations in two variables is a point of intersection of the graphs of the equations. That is where they intersect and then share a point. There are three different possibilities regarding the number of solutions to a system of linear equations, as you can see below. A system of equations in two variables could have just one solution, and this is what we call a consistent system. We'll talk more about that below. A system of equations in two variables could also have no solution. In such case, the equations represent parallel lines, and this is called an inconsistent system. So let's take those two together. If we have a consistent system, that's where they share one point. If it is an inconsistent system, they share no points, and that is because with the inconsistent system, the lines are parallel. And then you have the third type, and this is a system of equations that could have infinitely many solutions, and that is because they're the same line, and that is called a dependent system because they depend completely on each other. So let's just look at those three systems together here. So here, one unique solution, and you can see that we have two lines and they intersect. Now, this was not written in this lovely graphic that I found, so I wanted to make sure that you write this down. That's important, that this is a consistent system. Our next is where we have no solution, and you can see that's because line 1 and line 2 are parallel. That is an inconsistent system. And then infinitely many solutions if a system of linear equations represents the same line. So two equations could look very different from each other algebraically, but then when we go to graph them, we recognize that they have the same slope, they have the same y-intercept, they share all points, therefore they have infinitely many solutions, and this is a dependent system. So let's dive in together and look at an example. So we're going to work together to graph the two linear equations in order to determine if a unique solution exists. So this is something we've been practicing with quite a bit, is in order to graph these two lines, we need to get both equations in slope-intercept form. That is, we need to solve for y. So for the first equation, we need to apply inverse operations and subtract 2x in order to isolate y. So y is equal to negative 2x plus 2. And this is in slope-intercept form, where we can now identify the slope of this equation as -2. Now remember, definition of slope is change in y over change in x. So it is to your advantage to recognize that -2 can be written as a fraction, and there's two different ways we could write this. We could write it as -2 divided by +1, or another way to write this and understand movement is we could write it as +2 over -1. This helps us understand we're going to go down 2 and then to the right 1. This says we're going to go up 2 and to the left 1. Note, either way we look at it, -2, -2 over +1, +2 over -1, we do want to take a moment and note the slope is negative. And if a slope is negative, that means the line will fall. As x is increasing, y will decrease, and therefore the line will fall. Looking at our next equation, we have 5x plus 3y equals 9. Now we need to get y alone, but the first thing we need to do is remove 5x from the left side by, again, inverse operation. Since it is positive, we will subtract. So now we have 3y is equal to -5x plus 9. And then our next step is to remove the 3 from the y. Since 3 is attached to y by multiplication, we need to divide, but we need to divide everything by 3. So that gives us y is equal to -5 divided by 3 times x plus 9 divided by 3, which simplifies to be 3. So our slope is -5 over 3, which means we're going to go down 5 and to the right 3. Another way to write this is +5 divided by -3, which means we're going to go up 5 and to the left 3. Now to get started with graphing each of these linear equations, we need to not only identify the slope, but also the y-intercept. So the y-intercept for our second line depends on the constant, and so our y-intercept is 0, remember always as a point, comma 3. So the y-intercept for the second line is 0, 3. And then the y-intercept for our first equation is 0, 2. We're going to label x, label y, and scale in all 4 directions. And this is our starting point, 0, 2. So 0, 2. And then our slope tells us that we're going to go down 2 and to the right 1. And I can keep doing this. Down 2 to the right 1. Now eventually I'm going to run out of space on this grid, this Cartesian system. But remember, I could also go up 2 and to the left 1. And do you notice that all of the points lie on the same line? They are collinear. Now I'm going to take a straight edge, lay it very carefully on all of these points. I'm taking my time. And then I'm going to join these points. Use an arrow on each side, each end, and then graph the next line. So the next line, as you can see on your paper, has a y-intercept of 0, 3. Now that is not a point of intersection, is it? Because they have different y-intercepts. and then with a slope of -5/3. If I go down 5, 1, 2, 3, 4, 5, and to the right 3, 1, 2, 3, I've crossed over my line, but that is also not a point of intersection. So I'm wondering if I should actually go up 5, 1, 2, 3, 4, 5, and then to the left 3, 1, 2, 3, and that is it. That is our shared point. So that is a point if we graphed both the first equation and the second equation correctly. That is the shared point. That is the point of intersection. That is our solution. So 3 things that we're going to now do. We're going to recognize that the system is consistent because we have 1 point. System is consistent. 1 point. The solution is -3/8, but we want to make sure that we graphed both equations correctly. So we're going to actually check this. And to do so, we're going to take the first equation, which is 2x plus y equals 2. Notice I'm always going to the original, and I'm going to let x equal -3 and let y equal 8. So x of -3 and y of 8, which gives us -6 plus 8, which is 2, and -6 plus 8 is indeed 2, which says the point that we believe is our solution is a point in the first line, but that's not good enough. We need to make sure it's a point of the second line as well. So second equation, we have 5x plus 3y equals 9. We're going to let x equal -3 and y equal to 8 again. And we're going to see if that combination gives us the output of 9. So -15 plus 24, is that equal to 9? -15 plus 24, -15 and 24 combine to be 9, which proves that the solution is indeed -3, 8. And for your homework, you have 3 questions here. For the system of linear equations, where each equation is written in slope-intercept form, determine the number of solutions and type of system. So for each of these, equation 1, equation 2, for questions 1, 2, and 3, you're going to determine 1 solution and consistent system, no solution, inconsistent system, or infinitely many solutions dependent system. So that is the same for question 1, question 2, and question 3, where the equations 1 and 2 have some variety. Make sure you go to your front page to help you with the solution.